So it's a great pleasure for me to speak in this conference in honor of Professor Dani. And first, I would like to congratulate Professor Dani on completing his, which number? On his 75th. Yeah, I didn't want to increase it unnecessarily, so just I was in a moment with birthday, and I really wanted to be there, but for some personal reasons I couldn't be there for a longer period and had to cancel. But I really miss being there. And okay, so what I'm going to speak today is something which is very much I learned from Professor Dani, and I started this kind of investigation and big part of this work when I was in Tata Institute. And it begins with what is called Dani Correspondence. Nowadays, this name is made famous by Dmitry Kleinbock, and he has really made great use of this observation of Dani in a lot of his amazing work. So let me just begin with one of the problems in the Diophantine approximation. You take any infinite sequence n in n to the power n, and we want to, for every lambda which is between 0 and 1, you define dt lambda, to be the set of all those vectors in Rn, so that for all but finitely many these numbers n1 to nn in this subsequence, in the sequence in n to the power n. I mean, you could take entire n to the power n also, but I'm just saying that you choose a particular subsequence in n to the power n. So for all but finitely many elements there, there exists an integer vector in Zn and an integer in Z, so that if you take inner product between Z and Q, you think of this Q as some kind of integral linear form evaluated at C in this manner. So C dot Q, and then you add this integer P, then the absolute value is less than or equal to lambda times the product of all these n1 into nn. And you put a condition that all the coordinates of Qi should be less than or equal to n. Okay, so under this condition on Q, you want to approximate this C by some kind of, a C in this sense as a form.
Nimish, what is n? Maybe an I?
Yes. Each ni. Right? So I equal to 1 to n, n is n1 into nn. Thanks. So Minkowski's variation of Dirichlet's theorem says that every element C can be approximated in this manner if you put lambda equal to 1. That's it. If you put here 1, then every n1 into nn, you can approximate in this manner. And Davenport and Schmidt said that can we, in place of 1, can we replace some lambda which is less than 1, and can we still get this kind of approximation for which kind of vectors? So they said that in fact, if you put any lambda which is less than 1, then this set is Lebesgue null. So really, you almost all points psi, you cannot approximate in this manner. So they are not dt and lambda for any lambda less than 1. Okay, so this set is Lebesgue null. And Kleinbock and Weiss, so actually Schmidt, they didn't do exactly in this form. Kleinbock and Weiss did a somewhat more general formulation of this, not just with forms, but also with more general matrices. But but basic idea is as follows, and that is where they recalled a paper of Dani Correspondence, which is there in a paper of Dani on divergent trajectories in Crilly journal. I'll talk about it later in the next week. So you look at a diagonal matrix, which is whose corner top entry is just product of all these numbers n1 into nn. And then in diagonal, you put n1 inverse to nn inverse. So this becomes a diagonal matrix inside SL n plus 1 R. Okay, so there are n plus 1 entries here. And then you take UXC as put 1 here, and then C1, C2, Cn here. And you choose a vector V as P and Q1 to Qn in Zn plus 1. So if you just multiply this UXC with V, you apply this UXC to V, you get something like this C inner product with Qn here, Q1 to Qn, this inner product plus 1 multiplied by P, so plus P. And then here, all of this would just be Q1 to Qn. And then you multiply by Dn, then you multiply with this diagonal matrix in this manner. Okay, so this expression looks looks like this. Ignore the orange part. Now, if C is dt lambda, dt n lambda, actually I didn't write, but is in dt the sequence n. So if it's in dt n lambda, then it's equivalent to saying that when I write equivalent to saying there exists a vector V for every all but finitely many n's, for all but finitely many n like this, there exists a vector V of this kind, so that when you multiply like this, these numbers are less than or equal to lambda because I divided by n1 into nn. If I bring it here, then this number multiplied by this is less than or equal to lambda. And then ni inverse times qi is less than or equal to 1. So ni inverse times qi is less than or equal to 1 for each I. Okay, so that means this vector really belongs to the first coordinate is between negative lambda and lambda, and remaining coordinates are between -1 and 1 to the power n, these guys. Okay, and you want that there exists such a vector V, that means this, and you want this vector to be non-zero because I assume that this Q should be non-zero. So this vector should be non-zero. So you want a non-zero vector here, so that when it intersects this set in a non-zero, I mean, it's non-empty. Okay, so some non-zero vector brings it to this set, and this should happen for so for each all large n in script n, there should be a solution. That means this set should be non-empty. So you change n, then this vector will change. So Dani observed that this Diophantine kind of condition, he did it in a different context, but Kleinbock and Margulis, Kleinbock and Weiss, they recognize that in this particular context, it would mean this. The Dani's correspondence would actually provide this information. So what do you want to interpret this as? So you look at the SLN plus 1 R modulo SLN plus 1 Z. I call it G mod gamma. This is G and this is gamma. And you take identity coset X naught. And you look at B lambda to be the subset of G mod gamma of the form G applied to X naught, where G is in G. So that when you take this linear transformation G applied to Zn, and you would like that to intersect this set in a non-zero element. Then B lambda is a closed subset of G mod gamma because this is a kind of closed condition. And X naught does not belong to B lambda because X naught is equal to Zn, and Zn, you cannot have a element inside negative lambda to lambda in the first coordinate. If you do that, then it will become Okay. Anyway, so this set, anyway, what one can show is that this set is, its complement of this set is a non-empty open set. That's all I want to say. That complement of this set is a non-empty open set. So therefore, if you say that C is in dt lambda, if and only if dn times uc times x naught belongs to this set B lambda. So these all, in other words, it says that if you just completely convert this question, meaning into something about G mod gamma, then all you say is that you take this uxi applied to identity coset in G mod gamma, and then you apply this diagonal element, then that should belong to this B lambda for all large n in n, or all but finitely many n in n. And that's all it means. Yeah, I have to put script n here. I keep forgetting actually. So Kleinbock and Weiss, they showed that if you take any absolutely continuous, Borel measure on Rn, and you apply that, so you take uxc applied to x, take any x in G mod gamma, you apply uxc to x, and then you consider this to be a point mass on this point. You translate it by dn, the diagonal matrix, and you integrate over c. So what you are doing is, in fact, something very simple. I made it very complicated. Say, for example, this measure is just given on some box in Rn. Okay, just take a box in Rn and put the standard Lebesgue measure there, and then you take u of that box applied to the point x, and then translate it by d of n. Okay, so you have this Lebesgue measure push forward on G mod gamma and then translated by dn. That's the measure mu sub n. Okay, so now so that theorem says that as n goes to infinity, and I will assume that all ni's go to infinity for simplicity, so that I can make a nicer statement. I assume that all ni's go to infinity, then mu sub n actually converges to the Haar measure on G mod gamma. Okay, so this is on Rn. But this is I assume this is a probability measure, and it's absolutely continuous with respect to the Lebesgue measure. So basically, you just take a box, and you just take a box like that. So then you prove that it converges to G mod gamma. So and then once you prove such a result, it tells you that for almost all C, if you look at the orbit, d times script n, so d times n bar, and you look at n in script n, okay, you look at this orbit, that means you take infinitely many these n's, then this set is dense in this orbit is dense in G mod gamma. In particular, it will enter B lambda complement, which is an open set, infinitely often for infinitely many n's, because somehow this is getting equidistributed in G mod gamma. So for one can deduce pretty easily using Lebesgue density theorem. You can show that for almost all x in Rn, it actually enters B lambda C for infinitely many n in n. And hence, you cannot have psi belong to dt and lambda for any lambda less than 1, because this is non-empty open set. Okay, and as you can see that in order for that to be inside dt lambda, it has to be inside B lambda for all large n. But here we are saying it is entering inside B lambda C, which is an open, non-empty open set. It may be very small, but it's still a non-empty open set. It enters there for infinitely many n's. While here you it should be inside the d lambda for all large n. So it is a contradiction. Therefore, this should be inside dt n lambda. It cannot be in dt n lambda for almost all C in Rn. So that is the concept. So we concentrate on this kind of result. So the proof of this result somehow uses something called Dani-Margulis non-divergence criterion. And in this particular, this kind of theorems, I'll talk about it later in next week, that Dani, based on this Margulis's non-divergence result, Dani developed a very nice criterion to see when a certain kind of measures don't diverge, don't go away to, don't diverge to infinity. And there is a criterion. Once you verify that criterion, you can show that by passing to a subsequence, this kind of measures will converge to some measure. And then because of these are expanding the horosphere using this diagonal thing, it will show that limit measure is invariant under the entire unipotent group like this. So you put all possible Rn here, and the measure will be invariant under entire of that thing. And then you can apply Ratner's theorem. And Ratner's theorem would tell you that limit measure would live in some kind of analytic subvarieties of G projected on G mod gamma. And there is another criterion due to Dani and Margulis. And I also developed part of it in my thesis, which I wrote under Dani and Professor Dani and Professor Raghunathan, that these limits are not, limits are zero. So there is a criterion which tell you that which, where this limit measure will converge to which analytic subvariety, or if it gives positive measure on some, in the limit on some analytic subvariety, there's something algebraic will happen. That is what this linearization technique tells you. So I try to prove similar kind of result inspired by work of Kleinbock and Margulis. And also, in fact, this paper also has certain component of what I'm saying here. They only talk about non-divergence in this situation, but not in general. So let's look at it carefully. Let phi be any analytic curve inside Rn. And you assume that this curve is not contained inside some proper affine subspace. Then almost every point of this curve is not in dt and lambda for almost all s in 0, 1, for any lambda less than 1. So what's the difference between these two? Here, we don't take a curve, but we take some kind of box like this. We take some kind of box like this, and we prove almost all points of this, we take the full Haar measure here and then translate. Instead of that, I just take some curve, which is analytic, and it's very curvy, so it's not inside a proper subspace, or even, it's not inside a proper affine subspace. So it's possible if you just take a curve, it is measure 0. So this theorem doesn't tell you anything because it's only about almost all C in Rn, but there may be a curve inside here, which may be an exceptional for this kind of thing. But what we prove here is that even if you take a curve, as long as it is very curvy, it behaves in a very generic manner, in the sense that phi of s is also not dt and lambda for almost all lambda, for every lambda less than 1. Okay, everything is dt and 1, but if you put, as soon as you put lambda less than 1, it doesn't belong here. So Kleinbock and Kleinbock and Barak-Weiss had proved something in much more generality, but they could do it when lambda can be arbitrarily small, close to 0. So that's a weak version, but this is a slightly stronger version. And in this case, if you just want to follow the earlier this kind of technique using Dani correspondence, what you want to prove is that you take x0, and then apply this u of s curve on this x0. So it is like you take this x0 and you apply curve u of s times x naught. And then you translate it by d of n whole picture. And this curve will become very long. And somehow you want to prove that that as n goes to infinity, this curve gets distributed inside G mod gamma in a very mixing manner that if you integrate any function on that curve, then it will become almost like the integration of the function on the whole space. If you write it in terms of measure, you call this mu sub n measure to be the measure on this curve, which is parameterized parameter measure. Okay, so that's why I put integration 0 to 1 ds, and you translate it by dn. You call it mu n, and you want to say that mu n converges to mu G mod gamma as n goes to infinity. To make our life simple in terms of notation, I'm going to assume that this ni goes to infinity for all I. Okay. So again, it's very similar to earlier, but the measure which is available for us to do equidistribution is much smaller, just a thin line. Proof again uses non-divergence criterion, Ratner's theorem, and linearization. And after linearization, you get some kind of algebraic condition. And to check that algebraic condition is very difficult, much more difficult in this case compared to the earlier case, because you don't have much freedom about phi of s. You can't change this phi of s in different directions, but only along the curve, which makes it a much harder problem. But we've managed to resolve it, and we did it. But now to apply this linearization criterion, one of the very important thing that we need is a growth property. And this growth property was noted by or abstracted by what is called C alpha property in this famous paper of Kleinbock and Margulis. So what do we need? We need the following. Our curve, analytic curve phi, is made up of coordinate functions phi1 to phi n. These are all analytic functions from 0 to 1 to r. And you look at all kinds of polynomials made up of these functions. You just make something like phi1 to the power k1 times phi2 to the power k2, phi n to the power kn, and then you want k1 plus k2 plus kn equal to d. You so fix some degree d, and you look at all linear combinations of this kind. Okay, so it's a finite dimensional space of functions you call phi d, and this space has the following property, that given any epsilon positive and given any alpha positive, there exists some beta positive, such that for any interval in 0 to 1, and these are all functions on 0, 1. So for any sub-interval of 0, 1, and for any f in this collection, if somewhere on this interval, the function becomes bigger than or equal to beta, then on the set where it is less than or equal to alpha, has measure less than epsilon. So you take this 1 over b minus a on this side, then the relative measure is less than epsilon. So only epsilon proportion of this interval can become less than alpha. So given any alpha, you can choose extremely large beta, so that once you know that somewhere on any interval, it becomes bigger than beta, then on that interval, it can't be less than or equal to alpha for more than epsilon of the measure. Okay, and you can do also converse part, that given any large number beta, you can choose very small alpha, so that the same thing happens. So these are the property we need for this collection of functions. The problem is that this property is not valid if we take all these coordinates to be C infinity. And because we could not do it for C infinity functions, we couldn't prove this measure, this theorem for C infinity curves. Okay, so that was a big drawback in this technique. And but because without this linearization technique, it's and you can also not do non-divergence technique also. Both of them require this kind of growth properties. So for polynomial function, this is very natural. If you take any polynomials of degree n, this is true. And or this kind of functions, analytic function space also, it is true. but you can't do it for C infinity functions. So the idea is to prove some kind of stronger result where we actually approximate our curve by, we want to approximate, we want to work with shrinking curve. And while we do the equidistribution, while we do the translate, we want to shrink the range on which S changes. You want to shrink it, and so that we can approximate it at a given point by its Taylor expansion and some finite Taylor expansion. And the error term, we want to choose good enough long Taylor expansion so that the error, when you expand it by dn, is very small. So how do we do this? So I actually forgot to write in my abstract that this is the joint work with Pengyu Yang. He's also going to give a talk today later in the evening. So everything I'm going to talk about is a joint work with Pengyu Yang. So Pengyu Yang actually generalized my earlier result for arbitrary semi-simple group G and for arbitrary diagonal groups, translating it, and but he still needs analytic curves. So now we want to do something for a C infinity curve in this earlier problem. So to do this, I need some notation. You choose, so because I had this n1 to nn, I'm just writing those n1 to nn by, I had this n1, n2, nn, right? So instead of that, it's really log of that. Instead of that, I'm going to call it R1 to R1T, R2T, and I even put it in order. So R1T bigger than or equal to R2T bigger than or equal to RNT. You choose them such that their sum is equal to n times t, and t is a very large number. So I write AT equal to e to the nt, negative R1T, negative RNT. So this is not a one parameter group. It's just some, for every t positive, you just put a number like this, okay? So you don't really need all positive t. You can fix a sequence and stop there. That's also okay. So you do something like this, write it like this. And it's an element of GLN plus 1R. And I'm going to assume that all coordinates go to infinity. In particular, this is the smallest one goes to infinity. And you write down UC as before that we had written. And note that when you conjugate UC by AT, then the first coordinate, it gets multiplied by NT. And when you write the inverse, it adds e to the power R1T. So it looks like NT plus R1T. And then here is NT plus RNT, the last one. So each coordinate, it gets multiplied by this number. And these are large positive numbers. So this goes to infinity. So it really expands this curve under conjugation. Now, you just pick some large k so that n1 plus r1t is less than or equal to kt. Once you have that for all, sorry, not n1, sorry, it's a mistake here, nt plus r1t is less than or equal to kt, okay? So this is how you choose some k. And this r1t has to be at least, r1t has to be at least t. Because total is nt and this is the biggest one. So it should be at least t, maybe even bigger. So therefore, this will be at least n plus 1. And you don't need more than 2n because total is less than or equal to nt. So r1t cannot be more than nt. So it is always less than nt. And so k is, maximum k you need is 2n, okay? So now this k is only not really very important, but I just told you. So let phi in Rn be a ck map. So you don't need all C infinity. It's enough to just have ck for some large enough k. And I'm going to approximate my curve using some Taylor expansion of order k. Now I assume that phi is k non-degenerate. So this concept was used by Kleinbock and Margulis to say that my function is some way curvy. What does it mean? For every s in 0, 1, you look at its up to k derivatives. phi1 to phi k. So k is n plus 1 or more. So there are lots of derivatives. Each of the derivative of phi is an element of Rn. Each of them are elements of Rn. So what I want is that all these derivatives span Rn. So in some sense, this curve, this phi is really curvy. It goes into all coordinates in some sense, locally. And if phi is analytic, this condition is equivalent to saying that one can say that phi is n non-degenerate for almost all but finitely many points. Okay. A phi is analytic and not contained in proper subspace. Phi of I not contained in affine. It means this. So my condition in the earlier theorem that phi is analytic and not contained in any proper affine subspace. Here I weaken this condition by saying it's C infinity curve, and it's very curvy in the sense that k derivatives span Rn. Okay, and suppose G is contained in L and acts on L mod lambda, where L is some Lie group and lambda is a lattice in L. So we want to make it more general. We are not going to just look at action of G on G mod gamma, but little bigger. G is contained in L, and you look at the homogeneous space L mod lambda, and G acts on L mod lambda. Now, you take any x in L mod lambda, then by Ratner's theorem, Gx closure is a homogeneous space, very nice space. Mu, and you call mu sub Gx closure to be the homogeneous probability measure on this Gx closure on the space L mod lambda. Okay. So first theorem is that we prove says that in fact what we were expecting is correct in this situation, namely you take the u phi s x, apply AT, and integrate f from 0 to 1 dx, then it converges to the integration of f see, everything is happening inside gx. Okay, so it can't be this measure cannot go outside gx closure. Okay, but in fact here that is saying that is actually equal to the limit measure is actually equal to this measure on gx closure. So for example, if L equal to G, then Gx closure equal to G mod gamma or G mod lambda. Okay, so it is really, it's little more general than before. And before earlier also for analytic curve also the same theorem was proved in this same form. The only condition we are putting it is weaker condition. It is C infinity curve or CK curve, and some this condition is happening. It's K non-degenerate or some non-degenerate. K can be any whatever large number you want. Okay, so how do we prove this? So again, the problem is as before. I cannot approximate like this. So the trick is to try to prove a stronger theorem. Namely, we prove the following. If we can remove certain countable set E from 0, 1, and for every S outside this countable set, so this is a Lebesgue measure 0. So for every S outside this countable set, I look at a very short curve. I take phi of S is fixed, okay? S is fixed. And then we make the curve only this much long, eta e to the negative t. So eta goes from 0 to 1. So what happens is that I had this curve. This is S, phi of S, and this is phi of S plus eta e to the negative t, or just phi of e to the negative t, and eta goes from 0 to 1. Now this curve is getting shorter as t goes to infinity, right? E to the negative t. So t goes to infinity, these curves become shorter. So it shrinks, and then you expand by AT. But expansion by AT is very high expansion. Its expansion rate is NT plus R1T, and in R1T is at least T. So the expansion rate is N plus 1T. So it really expands in all coordinates. Okay, it really expands in all coordinates. The contraction is very low. It's e to the negative t. Expansion is e to the nt. So therefore, it is certainly going to expand even if I take this short curve. And then if I integrate f on the translate of this curve by at, then somehow it will converge to, again, the Haar measure. And what we are saying is that this may not happen for every s, but if I remove a countable subset, then in the remaining set, we will be able to prove such a thing. And the reason for doing this is it will allow us to approximate phi near s by a polynomial function. I will explain that a little later. So it's clear that if we prove such a thing, then I break my curve into extremely short pieces like this. And then combining all this result, I obtain this. So theorem 2 will imply theorem 1. Okay. Now, how do I get these countables at E is a very tricky thing. So in fact, we need something else. What we do is following, that we make another definition. We say that phi is ordered regular at S if phi 1s to phi is. So you take any I between 0 and n, between 1 and n, and you look at the projection on the first I coordinates. Okay, so these are phi 1s, phi 2s are all vectors in Rn. You look at this projection on first I coordinates, then we are saying that the first I members or first I derivatives and project them to first I coordinates. After projection also, they should remain linearly independent. In the other words, if you take this first I, then project it onto the first I coordinate, then these vectors span Ri. Okay, so linear span of all these vectors is Ri for every I 1 to n. So somehow it's not enough just to have them linearly independent, all of them, but even coordinate projections should also be linearly independent. And this is equivalent to saying as follows, that you put the first derivative in the first row, second derivative in the second row, nth derivative in the nth row, and then divide by 1 factor, 2 factor because of Taylor expansion. It's convenient to do it this way. Then I know it's an element of GL and R if these are linearly independent. But on top of it, because they are, because they are ordered regular, in fact, it says that this element belongs to the big shell n minus diagonal times n plus. Okay, so I know GLN is a big shell. It contains n minus diagonal times n plus. Okay, this is a Zariski dense open subset of GLNR containing identity. So you want to make sure that these guys actually fall into this set, and you write it as some diagonal, and this element is in n plus. Okay, so this is in GLN, and our big group is Rn SLN plus 1. Okay, so it's just a way of writing regular, and an interesting proposition, which is not totally trivial, is to say that if phi is k non-degenerate for some k bigger than or equal to n, then in fact phi is order regular for almost for all s in 0, 0, 1 minus a finite set. So except for finitely many points, it's actually going to be ordered regular. It's as soon as it is k non-degenerate, and k may be very large, but still you only have to throw away finitely many points, and rest of them, it's actually going to be ordered regular. So that's a very nice fact. So essentially, we can assume that every point S, it is ordered regular. So I'm going to assume that phi is Ck and order regular at S. Once I have this additional condition, what one can prove is that you do exactly same kind of shrink around S, and you try to say what is the limit. Then it does have a limit. So limiting distribution is some measure mu. And how do you describe this measure mu? So this measure mu is essentially a homogeneous measure, but it's an integral of the homogeneous measure. You have some subgroup Q, very large group Q naught of this kind. Okay, here is Rn and SLN plus 1R. It's in SLN plus 1. Okay, and this is Q naught. You look at some particular element XS, which I will explain what it is, and you look at its closure. This is generated by unipotent one parameter subgroup, so its closure times XS, some element. Its closure is a homogeneous space. So you look at the homogeneous probability measure there. And then you translate by some particular element depending on this fixed S. And then you translate further by d eta, where d eta looks like a diagonal element like this. And you integrate over eta from 0 to 1. Okay. And that's all you do. And here also is a mistake. It should be eta. Yeah, so it's along eta. S is fixed. S is fixed. Okay. So you have this measure. This is fixed. This is fixed. But then you translate it by eta, by this element, and integrate the measure. So it's almost like homogeneous measure, but integral of homogeneous measure. And you can see from, yeah. So I think I may have made a mistake here. I think there is a little mistake in my writing. Let me repair it. Actually nicer than this. It is mu of Q naught times W Kn S times XS, then closure. So instead of putting this outside, it's here. Yeah, because I wrote this Q naught, that's why it looks like this. So actually this measure is invariant under the full unipotent group, the limit measure, because DNs are just normalizing this Q naught. So yeah, so the measure is actually invariant under this this Q naught, the limit measure, but it is really integral of these kind of measures. And what is XS? XS is so first I explained what is DN, then what is W of KNS. So W of kappa is simply you put kappa here, IN-1 and kappa inverse here. It's some kind of switch, some while group like element. And this KNS is the last coordinate here that you get in this expression. It's a very weird reason why this appears, nothing else. So that is what you get here. And what is XS? XS is U of Phi times X naught. It's not X naught, X. U of Phi S times X, because I have fixed this S here, and I'm taking any X in L mod lambda. So you take this X, and you apply that to V of S. What is V of S? V of S is just 1, and you apply BS on this side. This is upper triangular unipotent matrix, and that unipotent matrix we obtained in this expression. There is some BS. So this element makes this matrix into, you know, if you modify by these guys, it makes it in n minus and somehow more controllable in some ways. I will explain that later if it comes up. So what we show in this is that, in fact, at all but finitely many points, you actually do have a limit distribution of these measures to some nice measure, which can be described in this way. Okay, and this measure will depend on S. But interestingly, one can actually show, and it is also quite non-trivial to show, that all but countably many points, in fact, this measure is equal to already G invariant. So I don't even have to look at Q naught. So this is a mistake here. I should say that W, Kn, S, XS closure. This measure is really R measure, okay, for all S in outside a countable set. So that means theorem 3 will imply theorem 2. Theorem 3 will imply theorem 2 because I have thrown away countable set here. So really it is theorem 3 that we prove. Okay, that is the most important theorem here. And next, we can say something more. We say that that if we shrink slightly slowly, namely, don't write eta times e to the negative t, but you multiply it by eta times bt times e to the negative t, where bt goes to infinity, but you still assume that bt times e to the negative t goes to 0. So it's some kind of slightly faster, but the product goes to 0. This goes to 0, but bt goes to infinity. So you shrink slightly slowly, just slightly slowly. If you shrink slowly, then in fact for every point S where it is ordered regular, you straight away get equidistribution. So this way is another proof that's saying that if you call this theorem 4, then you can say that theorem 4 also implies theorem 2. Instead of shrinking, this you shrink slightly less. Okay, so this also works. And how do we prove all these theorems? So to prove these theorems, first we need to do this approximation. And how do we do this approximation? You take any fixed S and assume that phi is order regular at S. As we realize that as soon as phi is non-degenerate, it is order regular at all but finitely many points. So you don't worry about finitely many points. For the rest of the point, it's order regular. And so you try to do the Taylor expansion, AT times U of ES plus H. H is suppose something like eta times e to the negative t, then AT times U of S plus eta times e to the negative t times X. You rewrite it as AT times, AT times U of, you subtract phi S and then multiply it by phi S X here. And then you do the Taylor expansion here up to order k. Up to order n here, but in the end you will do it up to order k. And then you multiply by V of S inverse here, and then Vs here, and phi S X here. All of it together you call phi of S. And if you take this element across on this side, you conjugate, then because the way we had written this BS, the choice BS, if you take it on this side, then it becomes lower triangular matrix, this together. So therefore, you get a, because it becomes a lower triangular matrix, you can write it as AT times V of S inverse, AT inverse times AT times U of, you can write down U of Rs of H times some error, U of epsilon S of H times H to the power K, where K was very large number. Okay, and times, that's what it will look like, times XS. All of this is XS. And I take it on the other side. So you do some kind of conjugation, and this Rs of H will actually look like summation KIS plus some little o of H times H to the power, or so maybe it's an order of H times H to the power I times E to the I equal to 1 to N. And this part, again, you bring it on left-hand side, because U is commuting. So I can bring it on this side through AT. So AT will expand this, but you realize that AT times U of epsilon SH times H to the K negative t actually goes to identity as t goes to infinity, because h is equal to e to the eta times e to the negative t. So h to the power k is kt, and kt is bigger than nt plus r1t. So it's bigger than all those expansions. So when you expands it, it's going to go to identity. So this part will not matter. This part will not matter, and it's going to be a polynomial like this. So really, and this will also go to identity because this is lower. This element is upper triangular unipotent, and R and T were ordered in such a way that this will also go to identity. So really, this is just this will look exactly almost like 80 times u of RSH times XS, and this is what you really need to understand. And where RSH is a polynomial of degree at most k in H. That means k a polynomial degree at most k in eta power k. T is fixed. Every t we are going to think of it as a different function, and it's really going to be a polynomial eta. So in some sense, I reduce my problem to the problem of polynomials, but I'm now going to have this polynomial, but the range of it's going to shrink. H is equal to theta e to the negative t. Okay, so it's actually shrinking, and we show in the end that so at this stage, maybe I'll just show you some other part of the note that will help. Just give me a second. Yeah, so at this stage, we only need to work with this expression, and it's polynomial of degree at most k in n. And to apply linearization, let's see if this is the one. Yeah, this is what I was trying to say. So, yeah. So when we apply a linearization and non-divergence technique of Dani and Margulis, we show that these measures mu sub t are, we want to show, apply non-divergence to show that they are pre-compact in the space of probability measures on L mod lambda. And in order to show this, one only needs to show the following, that if V is a finite dimensional representation of SLN plus 1R, then there exists some positive number C, so that for every vector V in V, if you look at this curve, U of R of eta e to the negative t, I'm fixing my S. So I'm ignoring S. This is some kind of polynomial of the form. This is roughly, it looks like summation KIS times eta e to the negative t to the power k to the power I, and I equal to 1 to n plus some okay, and then KIS plus some little error, little o of h plus little o of e to the negative t, some such thing like this. But it's almost, but it is a polynomial of degree at most k. But most important terms are 1 to n, and then you write it in the way it is written here. So if you want to do this expression, all we want to say is that you take a vector v, apply your curve and translate by at, and take soup over all this eta in 0 to 1. Then this curve in the vector space translated by at is bigger than equal to c times norm of v for all large t. And this is all you want to prove. And we actually prove this. That is the main part of the whole game. And if this side is bounded somehow, so its sup is bigger than or equal to this, but for a given v non-zero, if it remains bounded, then we prove that if v will be fixed by a subgroup of this form Qn, where you have SLN in this coordinate and Rn here and 1 here. Okay, and you also know that this times Qn, if this is fixed by Qn, this time Qn is pre-compact in G mod Qn. That's pretty easy to see. It's just an algebraic fact. But this is hard. This is bounded, then we must be fixed by this. This is an important part of the theorem. And then we say that if V is not G fixed, so if it fixed by this, but yeah, this shows that it is fixed by, if it is bounded, then it is fixed by Qn. But we also show that if V is not G fixed, and if you apply beta t here, don't use only 0 to eta from 0 to 1, but you multiply by a very large number beta t here, so that beta t goes to infinity and this is still goes to 0. Then you can show that this number goes to infinity. That will ensure that it's equidistributed. It is non-divergent, and also linearization technique will ensure that it gets equidistributed with respect to G invariant measure. So that is also important part of the theorem. And I think my time is up. The proof has proof of these kind of techniques. So linearization technique will reduce my problem to a question in linear algebra. And here we make some nice, very nice algebraic observations, and use some new technique developed by myself and Pengyu Yang, and using that we achieve all of this. But that will become very technical at the moment. So I'll stop here, and again, thank you very much for listening to me.